Over 141 billion cubic feet of wood are consumed worldwide every year.
From floors and walls to desks and kitchen cabinets, this material is present in nearly every modern living and working space. Yet to meet such enormous demand, we cannot rely solely on natural forests.
That's why the industry has turned toward a more sustainable strategy, producing engineered wood panels from scrap.
Through careful processing, resin blending, hot pressing, and shaping, discarded wood is transformed into strong boards, ready for use in large-scale construction and manufacturing. In this video, we'll explore how the industry repurposes wood waste to create a durable product that fits today's mass-market needs. Step by step, you'll see how technical precision, thoughtful planning, and resource efficiency are all brought together in every single panel. The modern industrial ecosystem generates vast amounts of wood waste
After every production cycle. Sawdust, shavings, and offcuts, once dismissed as
worthless leftovers, were often burned or buried simply to clear space, releasing emissions and polluting soil.
For the wood recycling industry, however, this is a valuable feedstock ready to be collected and given a new life. Worldwide, more than 44 million short tons of wood waste are gathered each year from sawmills,
processing plants, and furniture factories, at specialized treatment centers.
This material is screened to remove metals, plastics, and other contaminants, then dried to achieve optimal moisture levels. Careful particle size classification ensures input consistency, laying the groundwork for strength and stability in later applications. The impact of this recycling model extends beyond cost savings. If left unused, the material would force the industry to harvest an additional 6.4 billion cubic feet of roundwood annually. The loss of more than 2.5 million acres of forest, or over 4,000 square miles, an area nearly equal to the state of Connecticut. That scale of ecological
Recycling wood waste is not simply about managing industrial leftovers. It underpins a circular model of manufacturing,
where value is preserved, resources are renewed, and waste itself becomes the foundation of a new production cycle.
once sorted and cleaned of contaminants such as metal, plastic, or non-wood debris. The collected waste is fed into chipping systems to achieve uniform particle size.
The goal at this stage is to produce wood flakes or fibers, an ideal structure for bonding with resin and forming panels with mechanical stability. Depending on the type of board being produced, particle board, OSB, or MDF, the factory may use drum chippers, disc chippers, or high-speed mills. The input material can include short logs, cut-offs, broken boards, or even branches, as long as all impurities have been removed. The chipping blades, made from hardened alloy steel, rotate at speeds between 500 and 1,000 RPM, continuously cutting the material into standardized pieces, typically under 30 millimeters for conventional particle board.
This stage is more than simple mechanical processing. Oversized, thick, or irregularly shaped particles can cause voids,
weak bonding, or warping in the final panel. Conversely, particles that are too fine increase resin consumption, raising costs and reducing stability. To balance these factors, most chipping systems integrate vibrating screens directly after the cutting process. This allows on-the-spot reclassification. Undersized or oversized material is reprocessed, while properly sized particles move forward to the drying stage. Immediately after chipping, the properly sized wood particles are transferred into drying systems to bring their moisture
content down to an optimal level before resin is applied. This is one of the most critical steps, directly affecting bonding quality, dimensional stability, and the durability of the finished board. Depending on the type of panel being produced, the target moisture usually ranges between 2% and 8%.
Excess moisture makes resin adhesion difficult, weakens bonding, and can cause blistering during hot pressing. On the other hand, if particles are too dry, they become brittle, increasing material loss and requiring more resin than necessary.
Drying is typically carried out using forced hot airflow or rotary drum dryers, with temperatures carefully controlled between 300 degrees Fahrenheit and 570 degrees Fahrenheit. Inside the sealed chamber, lasts only a few minutes, but demands highly precise control of heat and humidity across the entire material flow. To ensure uniform moisture, the particles are automatically cooled and pass through inline moisture meters after drying. Any batch falling outside the acceptable range is either rejected or sent back for redrying, guaranteeing that only qualified material proceeds to the next stage. After being dried to the required moisture level, the wood particles pass through screening systems that classify them by size. The goal of this stage is to ensure that each group of particles is uniform and suitable for the different structural layers of the panel, from the dense core to the smooth surface. The screening system typically consists of multiple vibrating decks, fitted with meshes of varying sizes. Oversized particles are separated and sent back to the chippers for further reduction. Conversely, particles that are too fine, often referred to as wood dust, are removed from the flow, as they increase resin consumption and may compromise the board's strength. The material that meets specifications is divided into two primary fractions: fine particles for the surface layer and larger particles for the core. By controlling particle size at this stage, manufacturers achieve a more stable resin mix, reduce waste, improve bonding performance, and ensure the mechanical integrity of the finished panel. After being sorted by size, the standard wood particles are transferred into sealed mixing chambers,
where they are coated with adhesive resin. The most commonly used binder is urea formaldehyde, sprayed in a fine mist through high-pressure nozzles to evenly coat each particle without clumping.
The resin ratio is tightly controlled, typically between 8% and 12% of the dry weight. In certain formulations, factories may also introduce additives at this stage to improve moisture resistance, fire retardancy, or protection against fungi. By the end of mixing, the blend of wood and resin has a stable moisture level and uniform bonding strength. After resin blending, the wood-resin mixture is evenly spread onto a moving belt in multiple layers, typically with a thicker core layer in the center and two finer layers on the surfaces. Automated spreading systems regulate both flow rate and material density, ensuring even distribution in both thickness and weight. The layered mat is then passed through a pre-press system, where hydraulic rollers compress it under ambient temperature. The main purpose of this stage is to lightly compact the material. It also allows the first bonds between wood particles and resin to form more uniformly before the mat is subjected to the extreme pressure and heat of the hot press. Although the pressure at this stage is significantly lower than during final pressing, it is still sufficient to lock the structure in place temporarily. This prevents displacement during transfer into the hot press and improves the dimensional stability of the finished panel. After pre-pressing, the raw mat is fed directly into the hot press, the stage that determines the mechanical strength and dimensional stability of the entire panel. This process combines high temperature and heavy pressure to compact the wood particles and trigger the curing reaction of the resin. Depending on board type and thickness, the hot press operates at temperatures between 280 degrees Fahrenheit and 430 degrees Fahrenheit. Pressure can reach up to 600 pounds per square inch. Pressing time ranges from 2 to 6 minutes. During this period, the resin shifts from liquid to solid, forming durable bonds that lock the compressed wood particles together. The press is fully automated, with sensors continuously monitoring temperature, pressure, thickness, and pressing speed.
As a result, each board leaving the press achieves consistent hardness, flatness, and stability.
Immediately after leaving the hot press, the panel is still in oversized form, often larger than the final dimensions, to ensure full coverage during pressing. Before entering the cooling stage, it passes through automated trimming systems that remove unstable edges and standardize its size. These cutting units use high-speed sliding blades, operating with precision according to pre-programmed settings.
Panels may be cut down to standard formats, such as 4 by 8 feet, or tailored to specific product requirements.
Larger sheets for storage or smaller panels for immediate furniture processing. Trimming also eliminates outer edges that may have been unevenly compressed,
reducing the risk of defects in later finishing steps.
After being trimmed to the correct dimensions, the panels still retain extremely high heat within their core.
The strengthening. But this is not simply a matter of lowering temperature. It is a process of structural stabilization, releasing.
In modern factories across the United States and Europe, forced air cooling systems are equipped with massive rotary fans that support and rotate each panel while it still retains residual heat inside. Cold air is pushed powerfully from multiple directions, circulating evenly across the entire surface. At the same time, automated sensors regulate air pressure and temperature, ensuring uniform cooling between the core and outer layers. Any imbalance at this stage can cause uneven shrinkage,
leading to warping that cannot be corrected. Some U.S. plants even employ dual-direction cooling units to improve efficiency,
while maintaining high surface stability. Have you ever stood close to an industrial machine blasting out an intense stream of cold air?
That sensation of tense chill is in fact the perfect condition for the material to shed heat without damaging its structure.
By the time the panel exits the cooling unit, it has reached complete stability, ready for the finishing stages that follow.
Leaving the cooling line, the panels move directly into the sanding system, a set of machines that may appear simple, but function as the true finishing hands of the entire product. The rough surface of each board is fed through a series of high-precision sanding rollers, spinning continuously under tightly controlled pressure. With every pass, the outer wood fibers are removed, creating a smooth, uniform finish.
Beneath the line, high-speed dust extraction systems operate simultaneously,
removing all fine particles generated during sanding. This prevents heat buildup and avoids scratches from reappearing on the surface. The sanding heads automatically adjust to the thickness of each board, correcting even the smallest deviations left from earlier stages. More than just smoothing, this step ensures proper adhesion for the coating applied later. If the surface is not prepared to standard, the melamine layer can peel, streak, or crack during use, turning a finished panel into a defective product.
Any flaw, whether on the surface or hidden in the core,
can compromise the entire furniture supply chain. That is why quality inspection operates under the highest precision and strictest standards. Each panel is scanned with laser systems to check surface uniformity and to detect micro cracks invisible to the human eye. Immediately afterward, random samples are subjected to mechanical tests that simulate bending, compression, and torsion, the stresses a board will encounter in real-world use. Force measuring equipment records every deformation in real time, allowing engineers to evaluate resistance to warping, tensile strength, and the bonding integrity between layers. These data points are not only essential for on-site quality control, but also enable factories to fine-tune the process if any deviations begin to appear. The result is a product that reaches consumers with optimal stability, consistent in appearance and durability through years of everyday use.
Once labeled as certified, each panel is transferred to automated packaging systems.
Robotic arms rotate, grip, and stack the boards onto pallets in pre-programmed order, minimizing any risk of shifting during transport.
A layer of polyethylene shrink film is then wrapped around the entire load, securing it while protecting against moisture and dust.
In many large-scale factories, robots also apply barcodes to each batch, linking production data directly with warehouse and logistics systems.
After packaging, forklifts move the pallets onto waiting shipping containers, the starting point of a global distribution journey.
Yet even in this optimized process, challenges remain. Plastic shrink films are notoriously difficult to recycle, and distant markets often require additional shockproof wrapping, which increases packaging waste significantly. To address this, some manufacturers in the United States and Europe are testing fiber-based paper wraps or biodegradable films,
aiming to reduce environmental impact while maintaining the same level of protection during storage and long-haul transport. From raw timber to finished boards, the production of particle board is a chain of precise technical operations,
where every stage from sorting and chipping to drying and pressing is tightly controlled by automation and real-time sensors. Within this cycle, the role of wood waste is no longer overlooked. Fragments once discarded are restructured into a material of high strength, geometric stability, and direct use in construction, furniture, and large-scale manufacturing.
Yet particle board is more than just a material. It stands as proof of a different way of thinking about resources,
where value is created not through new extraction, but by reorganizing what already exists. Behind every panel lies a complex industrial system, still facing ongoing challenges, conserving energy and moving closer to a truly closed-loop process. If you're fascinated by smart industrial production lines and the rebirth of materials,
don't forget to like, share, and subscribe so you won't miss our latest videos.